right. I think this is working. We're just double checking all the different places here. It's amazing. I think it's working. Wonderful. All right. Cool. Okay, so this is fun. All right, we finally set up our stream and are able to stream on Twitch and YouTube and whatnot. And we'll probably stream them on some of the other platforms, hopefully sooner rather than later as well. But today is our first one, and we will be looking at how to use a probably very different kind of AI than what we've seen before, certainly very different from all the ChatGPTs and other large language models out there. And it's of course powered by Evara, so that's the full disclaimer, is that I am the CEO of Evara, and my name is Andreas, and I have a PhD. I have a PhD in computer science, and that I graduated last summer from the University of British Columbia here in Vancouver. And sort of as a vertical and related to some of my research, like the fundamental technology is known as probabilistic programming, and Evara is heavily involved with that technology as well. And we will see how we have built an engine and a system, an AI engine and an AI system that is able to integrate into all sorts of different platforms. In this case, it's going to be Excel, and we'll see how we can really leverage what we will consider like assumptions, modeling, crazy math, and automate how we can take even very little and scarce data to tell us something about the kind of assumptions and unknowns and the uncertainties that we deal with on a day-to-day basis when we're trying to make our decisions and in our planning procedures. In particular, this goes from anything from insurance to finance to personal budgeting, etc. And today we'll be looking at an insurance problem. And so I will move on right away to get right into it. Let's see here to get the demo started. And you'll see here I have it all prepared as we will go through actually building the model here in Excel, so you can actually see how the AI functions and what it's actually able to do. And I think this should be pretty good. We'll transition on to that. So here we are. This is perfect. Now, what we'll do is first we should describe the problem that we are going to be dealing with today. And the problem we'll be looking at from an insurance perspective is about, as you can see here, it's about figuring out if you are an insurance company and we are issuing out various different policies. One of the biggest problems we have to decide on is what premium should we charge the customers. Right, and this is useful, of course, for an actuary or for the insurers, as well as for the people on the other side. If you're taking on an insurance policy, this is going to be pretty helpful to understand how one might gauge the value of an insurance policy and what the risk, how that's quantified, that is involved with insurance policies. And we'll also be touching upon credibility, so we'll be very much taking the perspective from the sort of the actuary side of things, because this is where all the modeling and all the data lives, and this is where we want to be able to figure out and assess our own risk and exposure across many different portfolios and all of the different insurance policies that we are selling. And we need to figure out how we should charge individual policy takers from that. Now, we'll also touch upon credibility. I find this concept pretty interesting. I should also say I am not an actuary. I do machine learning, I do coding, I do statistics and probability, so I'm not an actuary. So feel free to correct me if I'm getting any of these concepts wrong. But bottom line is that, and I just need to check that the microphone is actually doing what it's supposed to do. So bear with me for a second while we check that. Let's see. Let's see here. Oh yeah, it works. Perfect. Brilliant. Just had to be sure. There we go. All right. So, no, it's not connecting. That's pretty cool. Anyway. But credibility seems to be a way to gauge our predictions or our models relative to the amount of information always that's available in the data. So for instance, if we want to predict, let's say, the expected cost for a particular class of policies, let's say it's car insurance or maybe it's house insurance, whatever it might be, we might look at estimating an expected loss. And if the data suggests that the variance and the uncertainty about that expected estimation that we would make ultimately is within a certain sort of error band or error range, then we'll say it has like high credibility, which I find kind of interesting. And I kind of want to challenge that a bit, maybe, because it seems to be a roundabout way and kind of not a truly probabilistic approach to how we might want to consider the future possibilities. Because if the distribution and the uncertainty around our prediction just is what it is, that doesn't say anything about the data not being good enough. It simply says something about that the variance in the way we sort of set up the problem just means that there are just uncertainties. We can't get rid of them. And the notion of credibility kind of implies that we just need to either maybe do better in terms of data, or we might need to do better in terms of modeling. And the latter is obviously true in terms of data. Well, that depending on sort of on the model and what we can infer from the data, which we can't just reduce that sort of uncertainty always. It really depends, I should say. So I find credibility to be a funny notion. I don't really know how one would actually sort of provide any value to this estimate, but there are at least some interesting sort of models that are considered in the sort of some of the resources that I have, looked at as I have been building out this model. So for the resources, it's this book here is called Loss Data Analytics, and it's available online, and I've been referencing that quite a bit. It's a lot of really interesting stuff. I'll show that in a second. And in particular, what I've been building, the ideas that I've been building upon here for today is the chapters 7 and 9. So basically understanding a little bit about how premiums are decided upon and what strategies to use in the insurance business, but also some of the models and the modeling that is being used in chapter 9, experience rating using credibility theory, etc. But let me just quickly here show you where that book is, so you can see the actual location. So I'll just transition over to that so you can see that. All right, let's get the thing up here. So here we are. I'm just going to send you this. Interesting. I'm just going to send you that here. So this is the link to the textbook. If you were to want to go and reference it yourself. And if we go back to it here again, you can see here, this is what they talk about. It's all about figuring out how you can do all sorts of different sort of modeling for actuarial purposes. And they have a lot of really interesting chapters here, all about from how the introductions and what the relevance is of an analysis is in the insurance and their associated activities, but also what is frequency modeling, what is goodness of fit of modeling. So this is the classical sort of regression-like models potentially, where you want to consider how well the parameters that you've learned fit to the data distribution that you're modeling. And they also talk about modeling loss severities, etc., so on and so forth. What's interesting is that, as I mentioned, probabilistic programming, as we'll see, what that really embodies is the idea of Bayesian inference. And we'll talk a little bit more about that here in a second once we talk about the problem at hand. But you'll notice here in chapter 4 that they also talk about Bayesian inference. And that's because when we want to consider our models and the assumptions that we make and the uncertainties that appear inevitably in such models, when we want to relate that to data, our observations, then Bayesian inference is probably the only normative way to connect uncertainties and what we'll consider maybe prior beliefs to observations. And we'll not go into too much of the theory there, because it's not, if you click on it here, you can see as we start getting into it, there is some math to associate with this, and the actual function here is actually fairly simple in its the way that it looks, as you can see. Right, it's actually just a simple multiplication and a single division, but it turns out that this is a very, very difficult mathematical problem in general, which is why doing Bayesian inference is not easy. And they talk about some of the pros and cons, and I'll also mention that in a second. But the point of the crux of the issue with Bayesian inference is that it's not that easy to deploy in general, unless you have a few special cases where you can do it analytically. And that's part of what we'll be able to see here, is that you can actually remedy some of those issues. And that is what we've done here with Evara, and that's what we'll be showcasing here, how that actually plays out in reality. And there's a lot of heavy math, obviously, that needs to be done. And that's also why Bayesian inference appears again in sort of the later chapters. And I won't go into sort of all of the details, but let's get back to the problem at hand. And instead, what we should remember is that, let's see, here we go, is that there is this book, there are these resources, you can go have a look at it if you want to see sort of more details, if you haven't already. I'm assuming if you're an actuary, you probably know a lot of this stuff beforehand. So let's dive into it. So like I mentioned, the goal here is that we need to figure out what the premium is going to be for a particular problem. In this case, we're going to consider car insurance. What we won't really talk about is what, for instance, the reserves should be, because of course, when you predict the potential future cost of a policy you want to offer someone, that can help you predict the price level that you should offer or charge. But that obviously ultimately still comes down to a supply and demand problem, where you need to really consider the potential customers and their willingness to pay. So the other side of things is that, well, there is obviously a premium you can charge, so that's revenue. But we also have, this is random, the system is random. We can't predict exactly what the cost is going to be, and it gets, increasingly more difficult, and it compounds across many, many policies in a massive and big portfolios. And the bigger and the more portfolios an insurance company has, the bigger the risk associated with the potential possible loss that will actually happen. So the question is, how much money should be kept in reserve for this insurance company to prepare for future claims, so that they actually have the money available, so they don't go negative naturally. And that is a risk trade-off, because the question is, what is your risk tolerance, and how much are you willing to have? How much do you want to have in your bank, and how much exposure are you willing to have? All right. So long story short, the problem is, for this use case, is how do we decide on a premium for a car insurance problem? So there is a company now, they have a lot of different vehicles they want to insure, and we want to charge them a single premium today, and that has to be based off of the expected loss that we would expect to see into the future. And there's many different ways we could go about this. So bear that in mind as we go through this example, that this is just one way potentially of doing this. And different industries and different insurance companies might have different policies in place for actually doing this. But this talks about how we could do it and how easy it actually is to do Bayesian inference, and how to approach these kind of problems much more intuitively than what might otherwise be described in the literature today. So in this case, we'll consider the rate as the number of claims per an unknown number of cars, right? So we'll say, how many claims do we expect to happen on an annual basis per the cars in the fleet? So there could be, maybe it's an expectation, a half claim per 10 cars, it's so on and so forth. And similarly, the exposure unit we will consider is then that question mark of how many cars, per how many cars, right? So we have claims per cars. And one of the problems we will be facing in this particular example, that's also mentioned in the in that textbook, the online textbook, is that the fleet size also changes annually, right? So again, if we go quickly back to the the book, and if you go to 9.4, this is where the problem is inspired from. This is a small variation to this problem, but as we can see here, and this is related to the Bullman-Straub credibility, but the particular problem we'll be looking at is essentially this one here, as is described. Sorry, the machine here is struggling a bit with all the stuff we have open. But you can see that we're looking at sort of a set of random variables, which for this x1 to xn, and x1 is year 1 and xn is year n. And we're looking at the possible losses that would be incurred from a particular policy holder, right? So that means every single year they have a fleet of cars and it's going to make some claims, and each claim is going to cost so and so much money for us as the insurance company, right? And one of the things they talk about is they assume that each of these events, right, each of these number of losses is IID, and that assumption is obviously one of the things they criticize. They say that's actually frequently violated. We will see how easy it is with the ability here in Excel to sort of address this particular problem, right? And the thing we would consider here is that in year 1, there is M1 cars in the fleet, and in M2 is then the number of cars in the second year, and so on and so forth. And one of the things we would then want to look at is what is the aggregated or the expected loss or the predicted loss every single year, and of course then on aggregate across, n number of years. And we'll see how we can set that up. But that's the problem in a nutshell. And then we will discuss different ways we could charge for this policy that we're offering. And in this example, we'll just assume they're offering it now, and we're not necessarily going to revisit that insurance policy next year. But we're just going to base the premium as of today, looking into the future. So we'll go back again to Excel so we can see how this plays out. There you go. Okay, so we're going to be considering what Bayesian inference is and how we're going to use it. And one of the reasons we're going to do that is because we're going to have a set of assumptions about this model that we'll be building out of this car insurance problem. And we'll also be looking at some data. So how many claims did this policy taker do make every single year for, let's say, for 5 years. So we have historical data, say, and we want to make predictions the next 5 years out in the future. Now, Bayes is the optimal way that will take those assumptions and uncertainties related to those observations and make an update to the entire model and all of the assumptions that we have and all the uncertainties, which will then carry forward into the future. So that's like Bayes predictions, right? And the benefit here is that by doing it, instead of using typical, let's say, black box models, let's say like some regression models or black box neural networks, is that we have full explainability, right? So the model describes the relationships between different components and different physical relationships that we can interpret and understand. And that's maintained or retained rather when we do Bayesian inference. So the updates we make carry the same meaning as they did when we built it initially. It's not like there is a magic black box in the back end that does various spurious things. There's no hallucinations happening here. And it means if we could just do very easy Bayesian inference, we spend more time on doing the modeling, which is where all of the explainability comes from, and where arguably a lot of the most valuable part of the expertise that as you as an actuary will have can be really expressed. Because Bayesian inference itself is nothing but really a mathematical exercise, but it's a very difficult mathematical exercise, which is also why in the book there are like various different approaches to estimating the sort of, let's see, the Bayesian expected value, right? So if we have a loss that's being estimated under Bayesian inference, we can also estimate the expected Bayesian loss using first order approximations. And that's because they can actually be done sort of more easily. The problem is, of course, they're approximations, and it turns out, well, we don't need to worry about that so much. And finally, the good benefit to this is that there's no overfitting. So we don't need to worry about the system overfitting to a few data points or even many data points, which is what typically other models are much more prone to. Now, it's obviously not a free lunch. There is difficulties, traditionally anyway, and that is doing all this inference is a gymnastic mess. If we were to, I don't think I have a good example here from the book, but let me see if I can just find some here while we look at this. But basically, doing Bayesian inference in practice requires us to do a lot of mathematics. And let's see here if we can find a good example where we have some of this stuff. I should have had this one thing prepared, but that's okay. We will find it as a good example, no problem. Let's see here. Oh yeah, here we go. Let's go and find. Here we are. I think we're gonna find some good stuff. Here we are. Just find some of this. There we go. And let's see here. We're gonna just move over here. So this is just to show very quickly, give a sense of what this stuff looks like. Right. So you can see here, like the math starts sort of piling up, and we can see there's some Bayesian stuff right here. This will give you the sense of what the name is, Bayesian premium here. But there's a lot of math, a lot of calculations, and this is comparing also different ways of calculating various different things. But there's a lot of gymnastic here that needs to be done. And generally, we would prefer not to spend our time doing all of that math, if possible. Many times it is useful, but we'd rather take that effort into building better, essentially, models. We'd probably be better off there, because it turns out that the Bayesian part can be automated. And that is what we'll be looking at here in a second. All right. So let's get back to it. Other things we'll talk about here is, one of the problems is that, premiums are largely determined by purely expectations, maybe some variances. And there are other utility functions that could be considered as a function of the loss to choose what would be the right price to ask for the policy. The thing is, what we really want to see, right, is the whole picture. Once we know all the possibilities, the distribution of actual future losses, all of these considerations are almost trivial, right? We don't need quote unquote guidelines. If we know what's going to happen with these uncertainties, then we can assess all of our risk and all the possibilities. And we can still calculate any additional set of functions from that, right? We can transform those losses into other things we might care about. We can compare that to our general exposure and map it into, let's say, our demand models elsewhere. It becomes much sort of trivial to do. If all we have is an expectation and a variance, that is, again, a set of simple summary statistics, which doesn't tell us the entire story. And finally, we have a lot of optimistic assumption that makes it feasible to do some of this stuff analytically. In particular, we'll see many times that an IID assumption shows up, which is just saying that everything is identical and is all distributed the same, etc. So we'll see how easy this becomes when we have a system sort of like this. I'm just going to make sure that this is nicely formatted here as well. If you want to do that, oops, it's not what I wanted to do, but I wanted to take this and clear that. Wow, perfect. All right. Some of the things we won't touch here are using black box modeling. It's just not the time for it right now, so we keep the example here more sort of digestible. We won't look at different utility functions. It's going to be pretty trivial to see how that is actually done, and we won't necessarily talk about optimization here either per se. So for instance, if you look at bonus malus, and that's in chapter, I think, 12 in that book, which is basically to say there might be a strategy you can choose where an insurer, someone insured, will go to a different sort of level with certain discounts on the premium, right? So if they don't make a claim the first year, they might be upgraded to the next level and get a lower premium and so on and so forth. But then if you make a claim, they might all fall all the way back to the original most expensive premium, or just fall back one level, whatever, right? So that can also be partly used to sort of introduce sort of more cautious behavior. And then it gets actually much more complicated and interesting, because now we essentially have to model how we would expect the people that are insured to react to such a strategy, because now we're not only being able to charge them maybe less, not just change the way that we charge them, but we're introducing a mechanism that will discourage them even more so from making claims, because if so, they will have a more expensive premium afterwards, right? So that is an interesting concept, and that's not clear that those two things are linearly correlated. And what we need to understand there is, again, connecting sort of, let's say, the premium price to what the people that are being insured, the population, how they're going to react to that, and that is going to affect what we expect is going to happen to the general transition every single year of all of the people that have been insured, how they might move around in these different levels. But we won't talk about that here. That's a further, much higher level of complication and complexity, but it's not actually difficult to do that with this either and do optimization, but it's just not we'll try to keep this a little bit simpler. I'm just gonna use the same formatting here. All right. Also, you will have to, of course, I was about to say, excuse me in terms of, it's a bit interesting, I think. Give me 1 second here. For this is being the first stream, and this really bothers me. Seems not quite right. We're just gonna clear formatting here. There we go. Thank you. Then we're gonna take that formatting and map it out here as well. Oh, there we go. Perfect. That was much better. Okay. Okay, so let's get into it. So car insurance. We could have gone through the model, but let's just dive right into it. So I've already prepared stuff here a little bit. And I'll put in all the things that we need to put in. But it turns out that if we're just looking at a single company, so let's suppose this here is company A, right? That's what we're looking for. Let's just put that up here so we can make this look very, very nice. And we are going to do it like we're supposed to. Right, so I'm going to format that, make the nice, beautiful alignment. Right, and we're going to say this is company A. We're going to make this, let's say, just 20, and we're going to make it bold. We're going to put a fat line under it. Wow, that's exactly what I meant, indeed. Here we are. Right. Okay, we're gonna then add some more space here. There we go. All right. So this is indeed what we're looking at. Okay. So the thing we will need to consider to build out this model is all the blanks that we have here. Right. So let me zoom in here a little bit. Don't need to look at it from so far away. Okay. So we need to fill in a lot of these blanks. But basically, I mentioned, we're going to be looking at a risk parameter and what the exposure is going to be. And we're going to model how the fleet size for this company is going to change. And then we're going to look at the total loss per claim, right? And we can see here we already prepared how we're going to make the predictions going forward. So we'll see how one can actually do this. And the numbers here are actually, again, inspired by that problem 9.4 from the textbook. And we'll see here how easy it is to actually make such a model. And then we'll see how easy it is to use some data, but we also have that. We'll see that in a second also. But let's just make sure that we can understand what these things are. So let's suppose this here, this is the labels. This is going to be A, B, and C, right? These will be nice to just remember. So the value, what we should consider here. So let's imagine again, what is A? So maybe actually let's call this R for the risk, and let's call this E for exposure, and this is going to be the annual fleet change. Much better. Wow, perfect. All right, so this is the expected claims per unknown vehicle. Now, we don't know what this is. Now, there's different ways one could find this, and the book talks about that as well. We might have some regression model here that uses certain characteristics about this particular policy. Take a company A, right? It could be the number of employees, it could be headcount, it could be growth, it could be location, so on and so forth. That might predict, let's say, the risk parameter, which is this expected number of claims that happens per single number of vehicles, let's say. But it doesn't necessarily really matter where it comes from. The point is, either way, that there will be some uncertainty associated with that prediction regardlessly. This might also be something from a sort of an aggregated database that just looks at the rough sort of expected number of claims per many different, like across many different companies. And we'll use that as our baseline. So this is our starting point. And now we'll go up here at the top where we can see it says Evara, right? And we can see we've sort of got a bunch of options here. If you haven't started it yet, this is what it would look like. It will just look like this as it's after Evara is installed. And this is the add-in that we have. And this is how you interact with it. The actual math and the computations and everything happens in an engine elsewhere. So what's actually happened here is that we've sort of changed how Excel actually operates. You'll see that as we go through this. But long story short, let's launch this. And so the first thing I want to do, and again, remember, ultimately we want to use all of this to decide on a premium, right? And this is how we'll go through it. So I want to add an uncertainty. So I'm going to add an uncertainty here first. And the cool thing about this is that you can't see this form that pops up, which is great. And that's because the sharing here with OBS doesn't capture that. And that is actually very much a shame. So let's see if I can't just quickly capture that window. Excel pop-ups. Okay, we'll make sure it's visible. Yes, sir. Yep. All right, hopefully this will actually do the trick. Right. That's what that one is. And we're going to add it. I forgot to add it at the right place. Great. Is it window capture? It's window capture. So pop up. Perfect. Now we're going to just add a quick group so I can put these together. Okay, we're going to change this name. Just give me one quick second here. Excel main window. Okay, perfect. I'm going to call this thing X go. And then we're going to put these into that. Whoops, there we are. And that is actually perfect. Okay, I'm going to remove this studio for a second here, and we are going to click on it. I'm going to move that, and I'm going to make this just a little bit smaller. Okay, so that right there is perfect. Okay, and I realize this doesn't seem to be perfect either, so we're going to remove that. So that doesn't happen either. That is good. And let me just double check here that this actually looks the way that we want it. There we go. We are back again. And I am going to double check that this looks the way it's supposed to do from this end. All right. Let's see here. I'm checking this and it actually looks pretty nice. Great. Okay. Here we are. Okay, perfect. So it's there. Good. I'm going to close that. That we'll see. Okay. So let's get back into it. So here we need to start to add in some of our uncertainties. And this is where we have our options here. So this is how you build a model in a sort of Bayesian fashion. In a way that's much easier. You don't need pen and paper for this. It's sort of baked into Excel itself, and you can do Bayesian inference sort of automatically. No matter what the model and spreadsheet looks like, you have complete freedom here. So the first thing we'll do is to have a choice of different sort of uncertainties that we could choose from. Here we have used a set of sort of naturally understood names. And the reason for that is, instead of calling them all by the distribution names, this might be a little bit easier to sort of get a conceptual idea of what these distributions intuitively might mean. Now, we have an advanced version of this as well, and I might look into that a little bit later in a future stream. But in this case, as they described in 9.4, we might consider a sort of exponentially decaying distribution, right? So in this case, we call that decline. And what that looks like, as you'll see, is it will gonna start from sort of up here, and it's gonna go down exponentially fast like this, right? So we have a scenario value, and we have the likelihood of it here. And in this case, if it's an exponential value, if we say supposedly that we expect there to be about one claim per some unknown number of vehicles, right? That looks like this. So we can just write that, and that is one. If we wanted it to be, let's say, even steeper with a different expected value that describes this distribution, we could, for instance, divide this by 50, in which case you can see the range here has been greatly sort of, the tail has moved out much further to the right. Or the other way around, if you want to make it much closer to 0, you can just invert the relationship there. You can see we got 50. The point is, it turns out that it's like 1 divided by the mean. That's really how you should think of this. That comes out of this. So in this case, it's just 1 divided by 1. We expect that to be one car, but it could be anything from like all the way up to 4, and it gets like really unlikely that it's like greater than 5 here. So let's add that uncertainty here. Boom. Okay, now we can see it gets populated here, which is great, and it shows that expected mean value, right? So this is the default behavior. Let's do the same thing now for the vehicle claim, and in this particular case, let me see here. Yep. So in this particular case, what we would consider is a Poisson distribution, right? So this is an occurrence, essentially, right? So we want to have a set of number of cars, and perhaps again similarly for the car, maybe we expect that there might be one claim in a year per 10 cars. Okay, so similar as before, if that is what we believe, which is quite reasonable. Again, this could either be what the actuary thinks. Again, this number would come either from just general experience from working with a lot of car insurance cases in a big portfolio, and this is sort of the assumption that they have, or they look at, again, aggregated data, or again, it becomes this sort of predicted model that comes elsewhere from. It could be a black box prediction as well. So in this case, you might say that we expect on average, kind of, that there will be like 10 cars that it was going to take for the, again, expected one claim to happen, right? But these are both unknown, right? They're both uncertainties. But we'll add this. It looks like this, so you can visually see what that looks like. We'll add it. And you can see the number shows up here. So these are those two expected numbers. Perfect. Now, the annual fleet change. So this is, again, now the number where we want to consider how many cars, more cars, how much is the car fleet going to grow every year. And here, now this is part of the model. Is not, again, this is not that important in terms of the particular use case, because this is not actually covered in the book. So this shows how easy it is to add something like changes in cars, because that's obviously important if you actually want to get an idea of what the future expected loss is going to look like for this insurance, for this company A. We don't expect it to be static, this number. It might grow, right? The company might be in a growing stage. So let's say, similar to before, we'll add this as an uncertainty. Okay. We have that here. I just need to double check so you can actually see this. Oh, you can. It actually worked really well. OBS is great. Okay, so Occurrences, rate, 5. Why? We expect there to be a growth of 5 cars in this fleet every year, right? But again, this number is also random. Actually, we don't know what this is, but this is what we would predict currently, right? So you notice that I've already written future here, right? Just to kind of tie it in with how to use historical data versus new data and whatnot. So the way we started here, these will be our, we might call these all of our assumptions, right? Or latent variables, right? That's what we have here. And you can kind of see here this text box, right? So we can do a text direction. We can do this like, say, 90. Across all of these, right? Let's see if I can figure this out in a nice way so we can actually get a sense of what this looks like. Okay, it's not happy with me. Merge cells, that is totally fine. Degrees, let's do 90 here. Perfect, almost. Can we just do this stuff here? Yes, we can. That's not what I want to do. Okay, whatever. Not what I want to do, but it does the trick, right? So we do latent variables, blah blah blah. Oops. Nicely done, and we'll do this as like that and like this. Perfect, right? So these are assumptions, right? All of these. So with all of these assumptions, this is our starting point. So this is kind of where we would begin, not having really any data. We're not looking at what this company has actually done historically. So it would be the starting point. Even with historical data as available, we will simply have to predict, quote unquote, backwards, as you'll see here, right? So you can see we're going to make now predictions for the past years, assuming we might be in 2019, because this is how the model works, right? The model is, it technically doesn't care about what day it is today. It cares about the relationship between a prediction we would have made in the past to the observations we have from that time and then forward. And then as we go forward in time, we'll use the new data that's available and add it to the model here. But we'll refer to all these as assumptions, right? So now let's look at how many claims might happen, right? Now, this is an interesting thing, right? Because we've talked about the risk and the exposure, and we say that we expect there to be, 1 per 10 vehicles. So that means if we want to predict the number of claims, we need to know, firstly, the number of actual vehicles that they have in the fleet. And from that, we want to actually predict the real number of claims that is being made. And so that, if you think of it, right, will be, first of all, the R parameter divided by E, the expected, the number of vehicles per 1 expected claim, right? And then we multiply this by the actual number of vehicles, right? Vehicles. That is what we would do. But then this is just the sort of, again, it's essentially different rates. This is the expected number of claims now, given that we know how many vehicles there is in the fleet, right? Because these two gives us the number of claims per number of vehicles. Then we multiply by the number of vehicles, that gives us the expected number of claims. So that means this is also going to be another Poisson distribution, right? Because that will then tell us how we should actually expect the real claims, number of claims to look like. So the starting point that we'll use is the number of vehicles. Now, suppose we are in 2020, so our model needs to start somewhere. So here we'll just assume we know, when that was back when they showed up at the office the first time, say, that they have 50 vehicles in the fleet. That's what we know. Oh, and I forgot to say that the loss per claim here is just assumed to be 15,000. This could have been another one of these. We call this the D value, right? Dollar value. Now, this could be another uncertainty. We might want to predict that as well. We don't know what the size is of each claim. That's going to be some other distribution. In this case, we're just going to say it's 15,000 to keep it simple. We don't want to have too many of them. But it's easy to do. I didn't leave this out because it breaks anything. I just wanted to limit it to some extent. All right, so now what we're going to do here is just like before, add new uncertainties, right? So I'm going to just make it a little bit easier to show we can do it like this as well. And here you can see we have all these other more complicated ones. If you look down the list here. the Evara dot whatever. So that's many distributions you can use. We just have a simpler interface to begin with. But in this case, we're going to say around, right? So we're going to say the number of vehicles is going to be, not the right one. This is for the next year. Now we're going to do this around. So the number of years here is going to be around the number we had above. Okay. Plus the annual fleet. And this is actually a good question. Is that how I ended up doing it? Just give me 1 second here. There we are. Here we go. Ah, exactly. Yes. Yes. I want to make sure that I didn't say something that was wrong here. All right. So what we're going to say here is going to be around. So we're going to say that it is obviously it's equal to, not like that. I don't want to be equal there. So hopefully this actually is well visible, but it's going to be equal to this plus the growth, of course, right? And we're going to make it, fixed. Oh, come on. Here we are. We're going to make it fixed. Now, we're also going to be saying that this is fine, but we also know that this model prediction here might be itself wrong, right? We can't just expect a constant growth. That's not how this stuff works. So we might say this like some sort of random walk a little bit, where there is a general trend that it grows by whatever this random number is, right? This number here. But in reality, I need to do this and finish this. But in reality, right, this is the random number that it grows by. Right now, it's just the expected number 5, but it could go up and down, right? So what we've done here, if you look at the function up here, is that we've set it's actually a 10% variation plus minus. So that's what the around tells us. And you can sort of see what I mean. If you go here, and I'll just rotate, but if you go to the uncertainty, you can see this here is around. And you can see here it says the expected number and the plus minus value. So we just say that there is a chance that this is going to go even higher or maybe a bit lower. Okay. Now for the claims, we're going to do that thing that I just described, right? So we're going to be saying this is going to be Evara.occurrences again. And this time it's going to be the number of cars. Okay, C11 multiplied, in this case, by, yeah, I might want to do it this way around. So we're going to be multiplying this. So it's going to be the risk parameter. Okay, and we're going to make it like this. Right, we don't want to change it. It's going to be referencing the same number divided by this number, right? The exposure, right? And we're going to multiply that by the number of cars, C11. That's it. Enter, right? Now you can see the number of claims here in the first year, again, we just showed you the expectation, is nicely the number of cars, which is 50. Now we say on expectation that we expect 1 claim per 10 cars, so that is indeed 5. And we see this is exactly the number that pops up. So that's perfect. So now we're going to do this for every single other year. So we're going to just expand it down. And we can see that this is great, right? It grows by 5, the number 5 every single year, number of cars. And we can see then similarly that it grows by half the expected, number of vehicles that was going to change our claim. So that if you grow by 5 cars, we should only expect a half claim more on expectation, which is what we see here, right? So this is how this grows all the way down. Now, similarly, it's very easy now to calculate the loss. That is simply, the number of claims multiplied by the loss, right? Done with that, easy. And similarly, we're going to drag that down. So this is perfect. Now we're going to do the same thing down here. And I purposely sort of divided this up. Like there's no reason why we had to divide this up like this. But we've done it because of, we've done it this way because of the fact that, let's see here. Oh, that's wrong. Here we are. This is going to be 16, 15, and 15. So we've just done it this way because that way we can sort of more easily look at where it is we have all of our predictions and what the historical data is supposed to be. Okay. So we're going to do that. And now, as you saw, I just copied the way to calculate this from the top all the way down. And we're going to do the same thing here. And obviously this says no number because, well, there is no number. Oh, come on. Here we go. There we are. And this is going to be 19. And that is perfect. And it's going to be 19 as well. Okay. Great. Now we also don't want to be doing this. This is not supposed to be nice and yellow. Let's just make sure we get this down here. Okay, I'm just gonna do, oops, I'm gonna do that. Perfect. That's what I wanted. This, and similarly, this does that and copies it down, and this is gonna go down like this. Wow, perfect. And similarly over here. Okay. So now we are going to be looking at this here for a second. Okay. Lovely. So this is actually basically all we need to do now. The model is actually done. And this is how easy it is to build out the model. We have everything we need, right? If you think of it, we are able to predict the number of vehicles, right, for this particular company A, how it changes every year, right? We can also predict the number of claims that we expect them to make, or like the actual number of claims that we are predicting for each year. And from that, we can deterministically calculate the actual loss that we would expect to see from this company, right? And this could be even more random in that it's not just random because of these two numbers or rows, but also because the actual loss per claim is not constant like this, but that would just be like, let's say, adding another uncertainty. But that is a whole other beast. It's like, how much does that vary? And that could be plus minus 5. We can add that sort of afterwards to see how that changes things. Anyway. Now, suppose we are now here at the end of 2024, or just now here in January, we're going to come out to 2025. And let's say we actually have data for this year. So let's go back to the actuals. So suppose we actually have these actuals. Now I'm just going to cover this because I haven't done it yet. Let's see if I can do this nicely. Group, yes, sir, we'll group that perfectly. Done, because we'll look at this in a second here. But let's say this is actually the data that we observe, right? So similarly to before, I'm just going to add something here to make it a little bit nicer. I'm just going to add this stuff right here, put it back in here, and put it in there. Beautiful, right? So these are the actuals. Okay, these are our actuals. And we want to use these numbers now to make and update our model and our predictions. Because right now it's a little, it's based on assumptions, which is good enough, and it's a starting point, but we want to use these numbers to actually make adjustments. And this is where you would traditionally need to start to do a lot of math, right? If you want to make out this model that makes these sort of predictions, you're either going to hard code all the expectations and whatnot, but then the model isn't very verbose. Here we have everything right there for us to look and explore and understand. And we can get all the answers we could possibly want in terms of making any decisions on what the risk is, how much reserve you should expect, right? The reserve is about how much is the expected loss going forward from this company. Even just, you can do it on just the next year or the next 2 years, etc. It doesn't really matter, right? As of today, the end of 2024, if we use our data, this is the best we can do, right? And so, for instance, if we wanted to look at the total loss going forward, right, the predicted future loss, that would be just this number, right? And if we want to consider it like, what is the predicted loss per total number of vehicles to kind of have a different exposure metric, that would naturally just be this number divided by now the sum of all the vehicles, because this is how one does that. Not entirely sure why, but apparently this is what you do. I'm not sure what to make of this number here, but obviously this is a matter of, I guess, how many vehicles in total have there sort of been across all these years that has been accumulated into predicting this loss. So I guess it's not a bad sort of metric, because the lower this number is in some way, the better, because that means you have insured constantly a lot of cars, and yet the loss, even though it might be growing, on the other hand, it kind of gives a measure of how, what's the right word to use here, sort of the risk that's associated with this particular company. Okay, so now we've done that, we've built that model, this is great. And the next question is, how do we use all this data? Because I want to figure out what these things are, right? That's really the problem we have, right? So I'm going to delete these because the labels don't really matter anymore. And we're going to take these and move that over here. I'm going to use this, and we're going to just want to change this a little bit, because I am not super keen on that. And I'm going to do minus 75. Not quite 75. I'm going to do minus 55. And we do minus 50. That's a great number. Not entirely sure I love that either, but that is what it is. Perfect. Assumptions. Yes, sir. And okay, it's not the best, but it does something, I guess. So that's kind of neat. Anyway, what if you do another one of these? Whoopsie. Ah, even worse. Amazing. Okay, we're gonna do it like that. And cool. So all of these are our assumptions. Now, we want to make slight alterations now to this stuff, because how do you take all this and use it with this data, right? We can't just replace them. That would be wrong. That says nothing about how to change our underlying drivers. That's really where all this comes from. And this is essentially what we care about. These are latent variables. This is what makes all our predictions into the future as well. So we want to update them. And that's Bayesian inference. It's telling us if this is our beliefs, right? Our priors, given our data, which is this, what's the new values for these, right? That is not a trivial task, and we can't just sort of fiddle around with these. You have to do a lot of math for it, and this is what Bayesian inference is. And this is where we either take out our, our piece of paper and we start to write a bunch of stuff down, right? So we'll start with P of X, and X is all our latent variables given Y. Oops. Right, this is how the calculations would have to start. This is the starting point. Right, is equal to P of Y given X. So these are our predictions, and X is still our latent variables divided by P of X. So this is our priors divided by P of Y. Generally, we don't know what that is, this P of Y. We know what that one is. We sort of described that. That's these in this case. And P of Y given X are sort of all of these down here, right? But in reality, and these ones too, but this could be much more complicated. It's not always the case at all that this is so nicely factored out. It could be all complicatedly sort of intertwined where, and this is kind of the case here, right? Is that one of these Y's depends on a previous Y, right? I mean, this year's vehicle depends on the previous year's vehicle and the change in the fleet. And so this affects multiple places and so on. And so there's a lot of math to juggle around here. And the bigger this model would get, and the more granular it is, and the more it ties in with other stuff in a bigger spreadsheet, maybe, the harder it's going to be. Right? And so we don't want to spend the time doing that math because it is defined this way. Right? And this is where the AI comes in. This is actually that branch, is that we can actually automate this, although it's not easy. Because the problem here is, again, it doesn't work with a sort of a fixed approach to this, because it depends on how we built this out. Right? What if I add more explainable variables here? What if we have different kinds of vehicles, not just a total number of vehicles? We want to consider different classes of vehicles. Well, then the model here changes just by virtue of the spreadsheet changing and our number of latent variables changes. And so if I have a single sort of online system that you can plug this stuff into, well, that would have to change because it's not fixed. Whereas black box model is very much like that, where you have a fixed set of inputs and then you get some output. If you want to change the inputs, you need to change the architecture and redo everything again. So we want to have something that can do this for us. And that is indeed what we allow you to do very easily. So that you can spend time on this stuff, which is what really matters. This is the understanding and the interpretation of it. And then don't worry about the maths of it. So what we can do now is we can go back up here to our top and look at this, add actual. We'll do that like this. We'll add the actuals, and these are our claims, right? This is what we observed. And I'll show you quickly what that looks like. We'll record it. You can see how we've referenced it. And we can now see the numbers here change accordingly, which is perfect. This is what we want. Like 65588, 65588. Perfect. We'll do the same thing for the vehicles here in a moment. And once we've done that, we can start to get the engine doing its work, and we can get the results from doing the analysis, and it'll do it for us. But to show and see the differences of it, let's remove these actuals. Perfect. And let's first consider the predictions, right? Because these are our loss predictions, a number of vehicles predictions and claims predictions into the future. Now I've cheated and actually generated a set of real future numbers as well that are directly related to these numbers here, right? So this is a data set essentially, and I've sort of simulated the future of what that would look like. So this is what actually happened going forward. Okay. It's example, but we only know this. So let's first visualize some of these changes, and I'm gonna cheat because I've made a plot or two over here. I'm gonna put that in. I'm actually gonna, oops. Have a bunch of these. We're gonna put them in here. Bam. All right. Perfect. So those are the ones, and we're gonna close this now. Perfect as well. And now we're gonna make sure, because I took them from somewhere else, so we're gonna make sure that we change these values. So we're gonna look at here, these are the real claims. And we're gonna edit it. And we're gonna change this. So the real claims, both beforehand and into the future, are these and these. Perfect. Now the predicted claims comes back from over here. Oops. Now the predicted claims, they come from here. And we want to be able to go back to the car insurance place. This takes forever. I can see we have a bunch of stuff and some shared stuff here. This is perfect. There we go. So car insurance claims predicted these ones and these ones, right? So historically and going forward. Done. Okay. Yeah. Okay. It doesn't like me. Must contains at least one value. We're gonna give it this value, and now we're gonna edit it. There we are. Let's go back. Claims and these. Enter. Perfect. Thank you. There we go. Right. This is perfect. And again, this is in a mode where we just show the expected numbers, and we're gonna do the exact same thing here now for the vehicles. We're gonna look at this, and we're gonna say the number of vehicles in reality was this, right? This is what really actually happened. And similarly for our predictions, we're going to do that. We're going to delete them, go back here, take the number of vehicles. Perfect. And we love that. And now let's do the same thing here with the losses. The real losses were these. Cancel that. This is perfect. The real losses were these, I said, and these. Wow. This is wonderful. And similarly, the ones that we're predicting in the losses were these, or rather are these and these. Okay. Brilliant. And finally, we want to just plot here the the differences. Okay. So these are the differences between what we predicted and what actually happened in the future. Right. So from 25 all the way to 29. Cool. Lovely. Okay, so we can see that here. So this is a nice visualization of it. Now, let's just go up here and start to look at what is more interesting, which is not just looking at all the means. We want to see the uncertainties unfold. That's kind of the point. And the first thing we can do is to go to this dynamic scenarios mode we see up here at the top. And if I were to do that, what we want to look at here is the changes, right? So you can see if you go back to the model, is that these numbers now are no longer the means, right? They're actually, as you can see, sort of an instantiation. It's a single draw from our model. It's a possibility. It's one scenario. And we can cycle through possibilities by clicking the next model. So you can see here exactly what happens, right? So this is a case where, and this is possible, there's no claims, just very few claims, right? If you go back to our model, we can see how low that is, both in terms of the vehicles, they didn't grow as much, but still grew. The claims were low, and so were the losses, and the differences still is now very, very large, because the reality is that we actually do have losses in the future, right? But as we keep clicking through, right, what you can see is that it's these numbers that are changing, and so are these, and so are these, and everything else that depends on them. And this is also just Monte Carlo simulation, if you think about it. And that's how easy it was to do that. And we can keep cycling through these and see all sorts of different possibilities. And similarly, if we go to our visualizations here, we can also see that, see how it changes and how the different predictions and possibilities are, like, you know, not close at all to the real, but it still seems to do something that is similar, right? You can see the model seems to perform pretty decently, relatively speaking, to what we actually observed here, right? But there's obviously more possibilities, and the problem is we don't know anything about what actually has happened. We have no observations and no evidence. And that is what these numbers here represent. So what we want to see is to use these data points, right? Which is the data points here. Oops. From 20 to 24, we want to use these blue data points here to kind of tie down and condition on that, the spatial inference, and make new predictions forward for the remaining years from that, and see how that aligns. Right? We would expect that to be much closer. That's what learning means. So let's do that. So what we can do now is we can go up here to the top and click Add Actual. I'm actually going to change the default value again because it's nicely visually to look at, so things doesn't change all the time. We're going to add these actuals, and you're going to see this form here, which is now an entirely new form. And since that doesn't show up, and I don't want to make, I guess I could make another. It's not that bad, actually. Let's just do that. So, this is what we'll call it. Okay, and that is perfect, actually. Brilliant. I'm going to put that here in the middle too. Awesome. There we go. Yep, it's there. Okay, this add actual is similar to before, and then we want to pick the actuals. Click there, and I'm going to go to this other side, and I'm going to choose them here. We're going to choose that, and you can see now they've been selected. I'm going to record them. And you'll now see these numbers, they change accordingly. And we'll do that for all the others. I will skip this one because this is the starting point for our predictions. So these are the ones that we didn't know. So we're going to do the same thing. We're going to do add actuals. We're going to record it. Pick the number of vehicles. There we go. Done with that. Recording it. Perfect. So now that's changed too. And that's all there is to it. Right. Now, this is the things we know. This is the things we want to learn from. So if we want to do a prediction now, what we can do is we can click Run here at the top. And when we click Run, it's going to automatically do everything it needs to do in the backend to make the changes necessary about these numbers. It's going to throw back examples. So that is Bayesian inference. It is essentially Monte Carlo simulations on steroids. It's scenario planning on steroids, where you're going to get a number of possible scenarios that are all generated accordingly to the model and the observations as specified by patient infants. So we can explore all those scenarios and make a proper assessment of the expected loss, the expected number of vehicles, claims, etc., and choose our premium accordingly. So let's do that. The first thing we want to maybe look at is how does this, risk parameter actually change now that we have this. So let's run it. So, oh, perfect, you already see it. So we can see here that we're generating scenarios, we see all the different forms, and then we have a scroller so we can go through them. And in this case, what we can see here are the possible scenarios, right? And what we'll notice here is that the standard mean is 1 and the standard deviation is now 0.3. And we didn't actually check what that looked like before, so we don't really remember the relativeness here of that. But let's look at the others as well. So this is still 1, so the mean is still the same. So that's actually pretty good. It's interesting. So we can verify that our initial assumption is not far off. What about the number of claims that we would expect? So now what I've done is I've clicked the number of claims and then I've selected this explore here at the top. And what we'll notice there, though, is that the mean is now 11, right? So we expect actually that there needs to be one more car on expectation. And finally, we have the annual fleet change. And similarly, we can look at that. We can see the annual fleet change now is 7.4 with a standard deviation of 1.3. So 2 like that squared is the variance, which means we expect that the number of vehicles actually grows more, given the observations. Right, so these are the changes that we've now needed to make. So it turns out maybe the risk is not as much in this risk parameter definition, hasn't maybe changed as much, but there might be changes to the number of vehicles per expected claim. So together, these two gives us another picture of what the risk actually is. And it could be that they grow more, and it's actually because there's more vehicles. And we can similarly explore the total predicted future loss. And we saw that it was pretty jagged, so I'm actually going to just change this and make some more scenarios to make it a little bit smoother. And this is how you control essentially the refinement and sort of accuracy of the system. And if you do that and we rerun it, we should see that this is going to look much nicer with 10,000 scenarios. It takes just a little bit longer to generate those. And we're going to throw them back. And here we can see that indeed it's about the same standard deviation. The mean is now perhaps estimated a bit better to be a little lower, 0.9. And as we now go down to explore the total predicted loss, oh, that's interesting why this looks like this. Well, we can remove this and toggle it on or off. There we go. Now we see the total predicted loss is on expectation across all those future years about $780,000, right? With standard deviation about 200,000, right? So, and similarly, we could look at the total predicted loss per vehicle. And that is all we really need, right, to choose our premium. So this tells us everything about what we should expect to happen in the future. So if we want to be fairly certain that we are not going to lose money when we take on this deal or offer a policy to company A, we should really use, I want to zoom in here, we should really use these set of scenarios to drive our decisions. So you see, if we're very, very generous, right, we might offer something down here, right, and say, we're willing to take on this risk, and maybe this customer is just not budging. Now, if we're willing to take on more risk in that, it's quite likely that the loss is going to be greater, right? This is the loss again, remember, B26 is the total loss for the next 5 years. Right, so that's going to be what we should expect. This is what could possibly happen from our expenses from this particular policy. And so by choosing, let's say here, this point to be the premium, that means there's a very good chance that the loss is going to be greater. But again, the premium is smaller, so maybe, you know, he's more likely to, this company A is more likely to buy the premium. Whereas if you choose something that is higher, they may be less likely, but on the other hand, we will hedge our bets a bit more and make it less likely that we will lose more than the premium cost, so we can cover our losses, right? So if you were to do the pure premium strategy, as it's called, right, the pure premium, then we would choose that should be equal to the you know, expected loss. If we choose the next 5 years, right, we could also just choose the next year and then we might reassess. But if you want to go by a premium defined over the next 5 years, if that's the term, then we would look at this picture, right? So the expected loss over 5 years in this case, right? Then that is in this case roughly equal to, as you can say, let's just say 780,000. Oops. Right. So to give this company A an insurance contract, we would charge them, if we go by the pure premium, about $800,000 for it. Which puts us in a situation where the cost, hopefully that didn't do anything bad. No, it didn't. Perfect. Which puts us in a situation where the, oh, I can't move this. This is fine. Which puts us in a situation where there's a decent chance, right, that the loss will be smaller, but there's also a decent chance it'll be bigger. Okay. If you choose that, that is like roughly the middle point here, right? Something like that, just to put the color there, right? Something here. So there's a good chance it's greater, but there's also a very good chance it's less than that. So it's a kind of fair point in that sense, right? And it seems pretty symmetric as well, which is also very good, which means we kind of both accepting the same kind of risk. There's an equal chance that they will claim more losses than they're paying for the premium, that, which is that's the total, you know, mass, or like all the possibilities up here, which is about the same if you just were to kind of count the total area here. It's about the same as what we'll see down here, so that we're both taking on the same amount of risk here by offering them the expected premium. But that's not always the case. It could be highly skewed. And so this is where we can really start to play around with supply, essentially, and demand, and discuss with the internal strategic team, how much risk are we willing to take on? And this is where it gets more complicated, where we might want to take some of these, you know, results and tie them in with other parts of the calculations and analyses and predictions of the organization, of the insurance company. Let's say we need to figure out what the reserves are required to be, because technically the reserves would really realistically have to be somehow reflective of the fact that there's a certain big chance that it's greater than this number, right? Right. So if you look at that, you can see that if this chance to say is about 50%, are we willing to bet 50-50 across many of such cases that this is what we'll be in the hole for, and we'll have to be able to pay that? Something like that. Somewhere up there. Right. So we can ask, what is the chance that it's greater than this, right? And we can ask, what is the chance that it's greater than another certain amount of money? What are the chances that we need to have at different levels, 100, 200,000, and so on and so forth, available? How much reserve would we need to have available to make sure that the chance is less than a certain amount of money? A certain amount of risk tolerance, right? So we could look at that and see what are the, the confidence intervals. And this is where we have the export cells here. If you click that, now you can't see this again. And so I'll add yet another window capture. Cell or port. Pop up. Yes, that's perfect. Yeah, look at that. It's gonna come in here. This is what it looks like. So we can choose. We can also choose to include the values from all scenarios, but we can certainly include the charts. And we need to select the cells. So we'll do that. And this is also not captured, so will be another one, which is the Excel input pop-up. Perfect. That is exactly what we want. So we can see where that one lives. Oops, it comes up here. Our export pop-up is that one. We're going to move this down there, and we're going to move this one down here as well, so we can see them all. Perfect. So here I have the it's right there. Perfect. I couldn't see it for a second. Okay, so here we have it. So we've got to select some cells. Let's go to the, let's see, this was B26, so that is this one. So we can pick this, choose that, and it will ask us if we are happy with this, and we'll export it. And it's actually going to open another window altogether, which has the numbers we want to look at. So I'm just going to copy those over just to make it a little bit easier to show what it looks like. There we go. So this is what that looks like. There we are. So that is just directly taken from this other sheet that has been exported. So we have access to those kind of results. Let's save that. But you can see here, and you can pick and choose the different percentiles, but you can see what the percentiles are, right? So there's a 25% chance that the, because this is the 75 percentile, there's 25% chance that the loss is greater than about $900,000. And if we subtract whatever premium we charge them, then we have an idea of that there's a 25% chance that this is going to be the risk and the reserve that we'll need to have available to us, right? In the delta situation, right? It's going to be greater than that. And that is where you can really start to consider what those reserve requirements are actually going to look like so that you don't go bankrupt. So that is bottom line what we need to consider. So that gives us the percentiles. You can also look at directly and say what is given this and the premiums you actually charge. So if we were to close this, so let's say we charge them, let's just say 650,000, which might change this a little bit, right? So this is total predicted loss, right? And so we might then down here have, this is actually a good question. I'm gonna add it. I'm just going to do this. Predicted loss, and we're just going to move that up. And that is just going to be moved up. Yes, sir. And this one is going to have no borders. Perfect. All right, so this here is then the profits, right? So we have the premium. I could have put this somewhere else, but not really that important. So let's say we have the premium here, and let's say that was indeed $600,000. Let's say then the profit is of course just equal to whatever we charge them for over those 4 years, like subtracted by that number, the actual loss. So that gives us the premium. Oh, come on. The impact of the premium. And where do I have that? Oh, this is getting annoying. Where is? I always get confused by that. Here we go. All right. So that gives us this number. So if we then choose that to be our premium, say, now we can then look at, similarly as before, run it again, as you can see here. Oh, it happens twice. That's great. Anyway, we're going to look at it again here. And what we're going to see is that this is what we should expect to happen, right? If we choose a certain premium. And this is where we won't do that today, but we might have another optimization stream later on, where we can choose the premium satisfying a certain criteria under this model. And this is where it gets even more interesting. But in short of that, for now, we can sort of just look at a visualization like this. And just like we said, it was about 880,000, I believe, if you looked at it last time. That is exactly what we see here. The mean is that we will lose, if we choose the premium to be 600,000, so 180,000 is the delta from the expected value, which is perfect, right? That's exactly what we see here. It's 180,000. But the variance is quite large, which means, and this is one of these that looks somewhat a little bit skewed maybe, but still fairly symmetric, but there is a bit of skewness. It's not too surprising. But we can see that there is a good chunk of negative profit where we just lose money. And so this is where, if you choose our premium, we should be prepared to expect with high chance that we'll be in the hole. And it's not necessarily going to be large, but there is a not an insignificant chance that it's going to be close to $500,000 with this one company. And you aggregate that over a lot of companies or people you give insurance to, then this can start to really ramp up. But essentially, you can see all the other things like from the book, and sort of becomes almost redundant at this point because we have the full picture, right? So I can choose to do any sort of utility function, right? I mean, I can choose to make this sort of any function of, let's say, the premium and the losses here, right? Say, I want something to be true about this utility. And maybe that's what drives, right? If this is the utility function, it could be sort of anything, right? There's many different suggestions also in the book, but bottom line is whatever matters to the particular insurance company, you can answer all of those kind of questions and decide what is the premium you should charge, or what are the guidelines generally that you would give the actuaries and when you decide what you should choose. What are the criteria? What is the threshold of tolerance where you say we are happy if the chance of losing more than $100,000 is less than, let's say, 10% or 5%, that's our threshold. And it needs to be true that the chance then of being less than 50,000 and so on and so forth, because that gives us an idea of like how much reserve do we have available to cover, and are we willing to risk it? And it's not clear that the best approach is to cover the worst case scenarios always, because that would be a way to do it, right? We could look at this and say, well, given that we've done this 10,000 times and we have 10,000 scenarios, we could just say, well, we really want to just take this because there is like a chance way out there. Right, so I haven't talked about this red one, but this red bar represents we can explore a particular scenario, and that belongs to this area, this negative about $150,000. So if you go back to the car insurance, you'll see this exactly. So this here is minus 200,000, so that's sort of somewhere in between. So minus 200,000, that's exactly what you see here. So you can see when we scroll here, you'll be able to see the different scenarios. You can export these as well and save them, so you can explore a particular case. So if you look at the worst case scenario, which is way out there to the left, the most greatest loss, and we go back, you can see that is exactly 1.185 million. And so if you're saying 1 out of 10,000 times, that's like the greatest risk we can see, and that was a possibility, we're going to make sure that we'll have this in reserve. But then again, the chance of that is very, very, very small. So it's not clear that that's the best strategy, because then all that reserved money is not going to do other work for you. You can't reinvest it into the business and make better products or have it grow elsewhere, right? So that's, again, another layer. You can look at what is the relative chances of investing that money and being able to recoup that as well. And it's not just about expectations. It has to include all these variances and standard deviations and the shape of all of this. And this is what we get here. And lastly, I wanted to show, you can see, because we didn't touch base on this, right? So you can see worst case scenario, the greatest error that we see in these plots. You can see that the claims, indeed, in worst case, is kind of and we should expect this to be the worst prediction out of 10,000. It's not great, right? It's fairly far off the reality, but it's not as awful as we might expect from the previous plots. Same thing, the number of vehicles, it grows a little bit faster than it should. The losses here, as you accumulate the two, kind of gets, compounded. This is why we see this peak here, and that's reflected in the differences between actions and predictions. And you can also see that the error is greatest here in 2028. So there might be a good reason to go and explore this a little bit more, what might have happened here in case we want to do that when we get to that point. But we can also look at it here and say, let's look at some of the possibilities. You can see compared to before that all the possibilities are much more in line with the reality of what is actually happening here in the future compared to before, where this was going all over the place from small to large, etc. And just so you can see, yeah, this looks like it's high variance, but the scale here keeps changing, which is why this might look a little bit sporadic. But that, I think, is gonna be the end of the stream today. This was great first run. I had a lot of fun, and I'm actually looking forward to doing this again. And I promise it'll be better and more efficient. This is for the first pass. It's the first time I've done a stream doing this, but I'm actually building this model here with you. Going forward, I want this to be a place where we can build models together. And if you want to join in and ask questions, you can certainly do that. And I'm happy to answer all of them. So this is great. Well, thank you. I will jump off this for now. I'll close this off, and hopefully we'll see you again soon. I'm hoping to do this probably maybe once a week, but I'll do it more often actually. This next week I have another model that I want to do, which is about investment for venture capital, which might be more interesting, and I'm going to be a little bit less maybe technical about that because it's a little bit more obvious, but it actually relates to reserves and having money available and being able to take on new investments or not, and not, again, having lots of data, which we didn't even talk about that, but clearly there's not a lot of actuals here that we are able to really leverage, which is kind of the magical part of all of this. But that's it. Thank you.